Hey, Dr. Tran, how you doing?
Hey Steven, I'm good. How are you?
I am tired, but good.
That's good. That's good.
It's been a long day. How are you guys feeling?
Oh, we're good.
Good.
How was your weekend? Did you end up watching that James Bond movie?
I did. I did.
How was it?
It was good. Um, and actually, we watched Spectre right before we watched the latest one, and it's really
Nice.
good. It's really good that we did because it's the latest one. I think a lot of it wouldn't really make a lot of sense, like like the characters and the like. It kind of follows it right after Spectre, and so a lot of the events from Spectre kind of show up in the latest one. So definitely
Uh,
recommend
all right,
recommend
That
cool.
seeing
makes
Spectre
sense.
first.
I'll make sure to do that.
Yeah, the Daniel Craig James Bonds tend to follow an overall arcing backstory that kind of ties everything kind of together. So
Right. Yeah.
it's
Hmm.
been it's interesting because it's kind of some of the only James Bond movies that actually really do that.
Hmm.
There's other ones that talk about Spectre or whatever, but they don't have this close of a tie-in in the story
Right.
from
Right.
edge to edge. So
Yeah, it was good. I think the funny thing too is that the Daniel Craig James Bond movies, they kind of follow a pattern where it started with Casino Royale, and Casino Royale was really good. And then the one after that, I honestly didn't even remember it existed until I looked at a list. It was called Quantum of
Quantum of
Solace.
Solace. Yeah.
Quantum of
Um,
Solace, yeah,
yeah, and so that one was not that good. But then the one after that was Skyfall, and that was really good.
That one was really good.
And
yeah,
then Spectre, I guess the reviews are kind of mixed on Spectre, but I think it was people rate it as one of the lower tier ones. But then No Time to Die kind of peaks back up, and so it has this kind of nice sine wave to it, or I guess it'd be cosine because it starts high,
yeah,
goes low, goes high, low, and then high again.
yeah. I went back and watched the God, it was over the summer, but I watched the James Bonds from Goldeneye when Pierce Brosnan did it, and then I watched that all the way up through Spectre, I think, and it's so different when you look at like the type of action that was in those older, you know, 90s and stuff like that. It's so different.
Oh yeah, yeah, yeah. I was talking to my parents about it last week too, and yeah, they for them, Pierce Brosnan's the only James Bond for them. I think they don't mind Daniel Craig, but I think Pierce Brosnan's going to be always going to be the only one.
The only one for them. I always liked Sean Connery.
Hmm. I haven't seen his James Bond.
Yeah, they're classic. They're far less. It's far less about action and far more about gadgets and swagger. But
Hmm.
it's he always had this really good James Bond swagger that made him a really good character.
Hmm.
You're gonna have to change your class from finite element analysis to film analysis.
I'd never taken a film class in college, and I kind of regret
Like,
not
oh
not
man,
doing it because it's um, yeah. I mean, I'd love to just I mean, there's the obvious one where you get to see movies in class, but I think just
yeah,
being able to talk, intelligently about movies and to comment more than just, I like this one because the actors, and the action was good. So I kind of wish I had that. I kind of wish I took that opportunity in college, but
Yeah, I was a film student before I was an engineering student, so I
that's
took
right.
all
That's
those.
right.
I took all of those. They were my favorite. I mean, sure, you analyze like film techniques and that kind of stuff and how it influences some of the stuff that we have today, and even with the James Bond films and stuff, like just their influence from the French cinema or German cinema or whatever is really, really fascinating. But you get to obviously sit down and have those conversations with people about, oh, this movie was so good, and you remember this, and oh, the characters were so great, and yeah, they they were some of my favorite classes. They're easy A's, but they're they were definitely some of the most fun.
Nice, nice.
Did did you have notes uploaded for this week?
Should
Yeah,
I not?
I haven't. I just opened up the page. So.
Okay, yeah, it's lecture note 09. Yep, stiffness method notes.
I see it. Can't believe it's week 8 already.
Yeah.
Oh man, that flew by so fast.
I don't know why this semester feels like it's going by so quick. Maybe it's just how busy I feel. Oh, Dr. Trent, somebody wanted me to ask you, like, because you're teaching FEA this semester, do you know if it's going to be offered next semester, or do you know if you're going to teach it next semester?
Likely not. And so with the way tech electives work here, they're typically only offered once a year. I did put in a request to offer it next semester too, just because I know that's kind of what we typically do, is offer in the spring. I know it wasn't part of the department's original plan, but I did put in a request to teach it next semester, because just because I love teaching this, and I know there's a lot of interest, from the students too. So usually I know that usually the department will add a bunch of tech electives later, kind of just based on the availability of the faculty. And so there is a possibility it gets added later, but I think it's not likely, just because it's being taught this semester, and they are kind of strict on, once a year kind of thing for tech electives.
Yeah. So that's probably, well, at least 410, but I know there's like isn't there a graduate level FEA 500 level course that's
There is. So there's 541, and I think I'm likely to probably teach that one too. But that one's going to be very different in nature, because that one's my I taught it, I think fall 2020, so about a year ago, and that's kind of my class to get people really into the implementation of FEA. And so we dive really deep into the theory, and we use MATLAB a lot to implement a finite element code. And actually, the final project for that class is, here's a heat transfer problem, implement the finite element method in MATLAB to solve it. And so it's very different in nature. I touch ANSYS a little bit in that class, just because I know there's requests for it, just because everyone that takes finite elements wants to learn ANSYS, but it's definitely not the focus like it is in this class. Yeah.
I gotcha.
Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Doing pretty good, Professor. How are you?
Good. Thanks. Yeah, I'm good. Thanks for asking. So first of all, let me say thank you everyone for being flexible this week. I know it was kind of a last minute change, and obviously you see that I'm in my home. I'm not on campus. And so, you might hear it behind me, but but my fiance has been coughing, ever since this past weekend, and so, we don't know if it's COVID or not, and so we're just trying to be safe, and the school has given me the freedom to teach up to 5 weeks virtually this semester in case something like this happens, and I thought I'd take that opportunity and just to make sure everyone's safe. And the nice thing about this week is that we don't have any ANSYS activity planned. Actually, we don't have another activity planned for a few weeks, I think, not until we get closer to the midterm. And so, I thought this would be kind of a good opportunity to do this. So, so thank you everyone for being flexible, and hopefully we still have a good lecture. Okay, and so with that said, today the class is going to take a little bit of a shift from the direction that we have been doing. Okay, so up to this point we've been focusing pretty much exclusively on ANSYS, and so we've done kind of 4 activities, and honestly we've done them at a pretty rapid pace. We've kind of been going like bang 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 bang, ANSYS. And along the way we've been learning a lot of the features and a lot of the kind of what I think of as the core knowledge that you need to use ANSYS effectively as an engineer. Okay, and so today we're going to take a shift. For the next few weeks, we're going to dive a little bit into the theory behind finite elements. Okay, and we're not going to do anything too crazy. And if you know anything about finite element theory, you know that it can get really crazy really quickly in terms of the math. And so we're not going to be going into the code of ANSYS and figuring out what that does. But I think there's some really core concepts within the theory that's important to know, especially for this audience here, where I know a lot of you are interested in just learning ANSYS and taking that to the professional world. But there's also a possibility to take this class as a springboard to maybe a graduate level class where you actually learn how to implement finite element theory, and you would work for a company like ANSYS. And so this class kind of has to serve kind of both of those purposes at the same time, which is kind of why I'm taking this detour in order to go into the theory. Okay. And so today, we're going to start really simple, and so we're going to start with springs, and so we're going to see how we can take a spring and then how that kind of sets the foundation for a finite element problem. Okay. All right. So I think that's all the announcements. So activity 4, remember, it's not due this Friday. It's going to be due the following Wednesday. So I gave you guys kind of a few extra days to work on it, because there is a lot to do in activity 4. Right. And so make sure you're working on that, and let me know if you have any issues or questions. Okay. Are any of you in the computer lab right now? No? Okay. Okay. Yeah, so I did oh, it's closed. Okay. I did ask the department to open the door. So I'll have to kind of send them another reminder for Thursday. And so I should have followed up on that today just to make sure the room's open. But I did ask the department to open the door just so that you guys can work on the projects. Just because I know for a lot of you, you're using the lab computers to work on the projects, and not having access to the lab is not good. So yeah, so I'll put in another reminder into the department to make sure the room's open for Thursday. Okay, it should be open tomorrow because they know that I teach a graduate class in there, and they should have it open, and then I'll make sure it's open for Thursday as well. Okay. Okay. So are there any questions before we get started for today? Okay. All right. And so let's go ahead and get started. All right. So the title of these lecture notes and kind of where we're starting from, finite element theory, is what I like to call the direct stiffness method. Okay. Okay. All right. And so, just to kind of set the stage again, what we're going to be talking about over the next few weeks are kind of the theory and the mathematics of how finite elements as a method is implemented. Okay. Okay. And believe it or not, the name finite element analysis or finite element method is not, it's not just referring to just one method. And so there's actually lots of different ways that you can implement it. And if you look into the theory, there's all different kinds. And part of the reason why there's lots of different finite element softwares out there. And so I know for this class we're using ANSYS, but another name you might have heard of is Abacus. And so that's another software out there that implements finite elements. And also SolidWorks simulation. And so even SolidWorks is getting into the game right now too, right? And so I can guarantee you that, I haven't looked at the implementations for those codes, but I can tell you that I know for sure that they've implemented it. They've each implemented them in their own ways, okay? And so with that said, it's going to be tough to go over, all those different types of implementation details. But there are a lot of what I like to call similarities between all the different methods. And so they do have some things in common. And so, I want to focus on what those things in common are. Okay. Okay. And so the three common details that they have that I'm going to focus on for today are things called the element stiffness matrix. Right. This first point right here, element stiffness matrix, is probably where you're going to see most of the variance between different methods. And so how the element stiffness matrix is formed is pretty different. Okay. All right, next is a step called assembly. Okay. And what that is basically we're going to be assembling a bunch of different element stiffness matrices together into one system. Okay, hence the name assembly. All right. And then the third similarity between all the different implementations is boundary conditions, right? And so boundary conditions is something you're all familiar with, right? And so those are the loads and constraints that we put onto our finite element simulation. And so I want to talk about basically when you specify those boundary conditions, how does that mathematically get implemented into the into the system? Okay. And so the implementation that we're going to be covering this week is something called the direct stiffness method. Okay. Okay. And so it's just one of the many implementations out there. Okay. But with that said, the direct stiffness method is probably the least useful one for doing any kind of practical problems, because it's really only suitable for really simple cases. Okay. But the reason I kind of talk about it is because of its simplicity, right? And so if we jumped right into some of the more complicated implementations, it gets really easy to get lost in kind of the sea of mathematical details, right? And so the reason I like the stiffness method, at least to go over in a class like this, is that the intuition behind it builds a lot based on your, what you kind of already know from structures and from physics, okay? And so this one has the highest, I would say, physical intuition. Okay. And so it's the easiest one to kind of pick up and kind of understand what's going on. Okay. And really, I just wanted to serve as a springboard for talking about these three aspects here, right? And so, when you're kind of first learning about finite elements, the theory behind finite elements in a class like this, I think, personally, I think it's a lot more important to kind of understand kind of this general process here of element stiffness matrices, assembly, and boundary conditions. Okay. And if you kind of jump right into one of the more complicated implementations, then this kind of overall process gets lost, and I don't really like that. And so, the direct stiffness method, even though I don't think there's a single code out there in the world that actually implements it for anything serious. It's kind of just a springboard. It's kind of just a way to get us, introduced to kind of what the finite element method actually consists of on an implementation basis. Okay. Okay. And so, using this direct stiffness method, it's going to let us skip a lot of the kind of the mathematical details. So we're not even going to see things like shape functions, which are core to a lot of really big finite element codes. But it is going to introduce us to the idea of these three items that I have listed above. Okay. All right. Any questions on this so far? Okay. All right. So let's go ahead and continue on. All right. And so let's start with the kind of the first item on the list, which is the idea of a element stiffness matrix. Okay. And the physical item that I'm going to use to kind of motivate this is, hopefully something that's very familiar for all of you, which is going to be a spring. Okay. Springs are really nice because their mathematical forms are very simple. They're very simple, but I think they encapsulate kind of everything that we need for a finite element method. Okay. All right. And so let me go ahead and draw a spring here. So we have a fixed wall like this. Okay. Right. We have an external force F right there. Okay. And then if we have our external force F pulling on the right of the spring, we know intuitively that the spring is going to stretch, right? And so the spring, maybe it has some initial length L, right? And so the initial length is just the length of the spring when there's no loading at all, okay? And then by stretching it with F, then the spring is going to displace by an amount D, okay? All right. And so the equation that we have to kind of relate all of these quantities is Hooke's law, right? And so we've been talking about Hooke's law actually quite a bit in this class, but this is kind of the spring version of Hooke's law. And so not the one that has Young's modulus and strain and stuff like that, but this is probably the first Hooke's law that you learn from your very first physics class, right? And so the idea with Hooke's law is that it's a relationship between an external force, okay, and the displacement, right? And so what Hooke's law says is that these two quantities are directly related to each other, right? And the proportionality constant between them, or you can kind of almost think of it as like a conversion factor, is the spring constant, right? So every spring is characterized by its spring constant K, right? And that basically is an expression for how strong the spring is, right? And so that's our very simple Hooke's law. And so F here is some external force. Okay. D here is the spring displacement. Okay. And this K is our spring constant. Okay. And so before we go any further, I want to kind of take a look at this kind of very simple formula here, right? And I want to kind of put each of the variables here, and I kind of want to shed a different light on them, because this simple formula actually, believe it or not, forms the forms kind of the basis for how finite element problems are set up, right? And so let's start from the left and go. Actually, we'll do kind of the ends first, right? So let's start with the external force, right? And so this external force, this is a force that you're applying on the spring externally, right? And so you can almost think of this, if we kind of relate this to our ANSYS problems from before, this is essentially like one of the loads that we have on our, on our system, right? Okay. Or in other words, it's a boundary condition, or it's a condition that we're applying externally on our structure, okay, that we can use to, get it to respond in a certain way, okay? All right, so now let's look at the displacement, okay? And so the displacement, you can kind of think of it as like the response, right? And so if you apply an external force to a spring, then the way it's going to respond is that it's going to displace by a certain amount, okay? Another way that we can think of the response is that this is basically the same as our primary solution variable. Okay, because if we think of this in terms of the ANSYS problems that we've done before, right? Think of what we're interested in solving for in our ANSYS, right? And so when we apply a load or loads and constraints on our finite element geometry, the first thing that we're interested in is, how does the structure respond, right? And the way it responds is through its deformation field, okay? And so this displacement here in this equation it kind of encapsulates that exactly, okay? All right, and so finally, let's look at the spring constant, right? And so the spring constant is obviously a property of the spring itself, okay? But if we talk kind of more generally, instead of just saying it's a property of the spring, we can say this is a property of the physical system that we're analyzing. Okay? Okay. Right. It just so happens for a spring that the only interesting physical parameter for a spring is its spring constant, right? At least in terms of determining its physics. But some other physical parameters that might be of interest are things like the geometry, right? And so what shape your geometry is, things like its material properties, right? And so we've talked about material properties quite a bit in this class, okay? And so all of those kinds of characteristics and all of those parameters for the physical system, they kind of fit themselves into this kind of relationship, right? Where you have this relationship between, an external force is on one side of the equation, and then on the other side of the equation, you have both the response and the physical properties of the of your physical system kind of multiplied together. Okay, and so as we kind of go about the rest of the lecture today, I want you to kind of remember this relationship and remember kind of the different perspectives for these all these different variables. Okay. All right. Any questions on this so far? Okay. All right. And so with that said, let's go ahead and take our spring here and let's kind of put it together in a different way. Okay. Because right now what we have is we have a spring that's fixed to a wall. And so let's go ahead and change this up so that instead we have a spring that's kind of freestanding. Okay. All right, so let's say that we have just an arbitrary spring like this, okay? And then at the ends of the springs, we have kind of the two nodes, okay? And so on the left, I'll call that node 1, and on the right, we'll call that node 2, okay? All right, and so on each of these nodes, let's say that we're going to be applying a certain force, okay? And so let's say that on node 1, we're applying a force F1, okay? And then on node 2, we're going to be applying a force F2, okay? And so now we have two of them because we've detached the spring from the wall, right? And so if we apply forces on both sides of the spring, right? So I drew them both in the positive direction here, just for convention's sake. But they can be arbitrarily oriented. Okay. And so I know that if we have a spring like this and we apply both forces in the same direction, then the spring is just going to translate, right? It's just going to move. But this is just kind of a general drawing here. All right, and so in response to the forcings, we're also going to have two sets of nodal displacements. Okay. All right, and so when we do this, and so when we have such a system here where we release it from the physical wall, we have what's now called a coupled system. Okay. Okay. And so all that really means is that we have two things that we want to solve for in this problem. And so essentially we want to solve for both D1 and D2, okay? But the values, the solution for D1 is also going to depend on the solution for D2, okay? And so that's what it means to be coupled. And so if you haven't heard that term before in a class, all that really means is that the solution of one part of the system depends on the solution to the other part, okay? And so for this particular problem here, the solution for D1 depends on the solution for D2. Okay. And of course, the vice versa relationship holds as well. Okay. And so when you have coupled systems like this, you can't solve for either one of these solution variables independently. And so you need to kind of solve for everything at the same time. Okay. And so you can't just go, one by one and solve for these, right? And so, this kind of begs the question of, what mathematical tool or what mathematical method do we have available to us that can actually solve for, multiple things at the same time, right? And so there's really only one answer for this, right? And that's a system of algebraic equations. Okay. And so our goal then is to basically take this simple spring right here and then turn it into a linear algebra problem, okay? And so in this particular case, we have two unknowns, right? And so we have D1 and D2. And so we're gonna need to get a system of two equations and two unknowns, okay? All right, and so that's what we're going to do on the next page. Okay. All right. Any questions on this so far? Okay. All right. And so to derive these two systems of equations, let's take inspiration from the Hooke's law that we have right here, right? And so from the Hooke's law that we have here, we basically have the relationship where we have our external force on one side of the equation And then on the right side, we have, the product of some stiffness constants multiplied by the solution that we want to obtain, okay? All right, so let's use same form as Hooke's law to derive equations. Right. And so I'm going to go ahead and just kind of stick this kind of straight away in matrix form, okay? Because we know that we're going to get two equations and two unknowns. And so one way that we can put this in a useful form is in matrix, okay? All right. And so what are the external forces that we have on our two node system, right? And our two external forces are F1 and F2, right? And so let's go ahead and stick that on the left side of the equal sign. And so this is basically the same thing as F is what we had, okay? And then similarly, on the right-hand side, we're going to have a vector, okay? Right, and so this is going to be a vector that has our two displacements here. So this is D1 and D2, okay? And so that's our D in our Hooke's law, okay? And so all that's missing here is how we're going to represent the stiffness for the system, okay? And so because we have these two vector representations of the external forces and the resulting solution, we have to have basically a 2x2 matrix here to make everything work, right? Okay. And so we're going to have a 2x2 matrix with 4 entries right here, K11, K12, K21, and K22, okay? And so this matrix right here is going to represent basically the stiffness properties or the physical properties of our spring, okay? Okay. And so our next immediate objective is then to find out, what are these values, okay? Because right now these are kind of just placeholders, and so I mark them as K11, K12, K21, K22, but those aren't actual physical things, and so we basically need to replace these with with physical quantities, okay? Keeping in mind that the only physical parameter that we know for the spring is its spring constant, okay? Okay. All right, and so let's start by taking our spring and let's pose some assumptions, okay? Okay. And so these assumptions are going to help us to derive the formula that we need, okay? And so first, let's go ahead and assume that our spring is in static equilibrium. Okay. And so the spring's not going anywhere, okay? Because we've mostly just been working on static problems up to this point, okay? And so in order for the spring to be in static equilibrium, then what that tells us is that F1, F2 here have to be equal in magnitude but opposite in direction. Okay. because we don't have any other constraints that are fixing our spring, right? And so in order for this to be, to make sure it's not going anywhere, then we have to, assume this. And so what we have then is, we have a situation like this where the external force, let's just assume that our spring is in tension, although it doesn't have to be. It can be in compression too. Okay. And so let's say that we have a tensile force T being applied on the right at node 2. Okay. And then on node 1, we have a tensile force pulling over to the left. Okay. And then we still have our spring constant here. Okay. And so this tells us that D1 is going to be, because we're pulling node 1 over to the left, that tells us basically that D1 is going to be pointing to the left as well. Okay. And then this also tells us that D2 is going to be pulling to the right. Okay. And so through this assumption of static equilibrium, we've kind of placed some constraints, on the directions of the forces and the, and the deformations. Okay. Any questions on this so far? Okay. All right, and so with this configuration in mind, let's go ahead and relate this back to Hooke's law. Okay. All right, and so remember, Hooke's law basically says that F is equal to K times D. Okay. Right. And so for this particular problem, we have a value for F, right? And so F here is going to be equal to T, which is the tensile force. Okay. Okay. And so K is still going to be K. Okay. And so D here is going to be interesting because the way that we're going to express D is going to be as a difference between the nodal solution values. Okay. Right. And so if we take this difference of D2 minus D1, this is basically the same as saying, how much the spring is deforming. Okay. Right. Because the difference in the nodal displacements is going to tell us that exact same thing. Okay. All right, and so in the end, by applying Hooke's law to this situation, we have this equation here that's going to relate, it's going to relate the externally applied force and the nodal displacements. Okay. All right. And so with that in mind, now what we're going to do is, now that we have this equation that relates T to K and D2 and D1, okay, now let's relate this equation to F1 and F2. Because remember, the equation that we want is we want to be able to relate F1 and F2 to the nodal displacements D2 and D1. Okay. Okay. All right, and so with that, let's go ahead and go back to our diagram here. Okay. And so for this one, let's start with node 2, just because we have T going in the positive direction. And so let's assume that the positive x direction is actually this way as well. Okay. Okay. And so assuming that the positive x direction is going to the right, in order for our system to be in equilibrium, then what we must have is F2 is equal to T. Okay. Right. And then on the other side, what we're going to have is F1 is equal to minus T, right? Because at node 1, then T is going to be going in the opposite direction, okay? Right. And so these two equations here that I've boxed, F1 is equal to minus T and F2 is equal to T, these are needed in order to maintain equilibrium, okay? All right, and so from here, what we can do is that, we can then plug in for T in these equations for F1 and F2, right? And so I'm going to take this equation, okay, and then plug it in for T here, and then plug it in for T right there. Okay. And so from this we get T is equal to minus K times D2 minus D1, okay? And then F2 is equal to K D2 minus D1. Just to make it a little bit more convenient, when we're putting this back in matrix form, I'm just going to distribute this negative throughout on F1, right? And so F1 is going to be equal to K times D1 minus D2. Okay. Right? And so now we have these two equations that relate F1 and F2 to D1 and D2 and K. Okay. All right. And so we're almost done with this derivation. And so the last step is basically just to take these equations and then put them in the matrix form that we have here, okay? And then that's going to give us the element stiffness matrix for a spring. Okay, so any questions on this? Okay. All right, so let's go ahead and put this into the matrix, and then we'll get our element stiffness matrix. Okay. All right, so let me go ahead and rewrite our equation. So F1 is equal to K times D1 minus D2, okay? And F2 is equal to K times D2 minus D1, okay? And so those are our two equations for our two unknowns, okay? And so we're going to assume that we know F1 and F2, right? And so what we want to do is we want to put it into the matrix form that we had before, which was F1, F2 is equal to K11, K12, K21, K22, okay? We have D1, D2, right? And so if we just kind of fill in the coefficients here, what we get is F1, F2 is equal to matrix K minus K minus K, K times F1, or sorry, D1, D2. Right? And if we extract just this matrix right here, right? Right. And so this matrix right here is a 2x2 matrix, right? And notice that it only has the values of this matrix are only comprised of just the physical properties of the spring. Okay. And so this matrix right here, which kind of incorporates that, this is what's known as the element stiffness matrix. Right. And so at this time, we can give kind of a more formal definition for element stiffness matrix. Okay. And so for an element stiffness matrix, this is a matrix that relates okay. This is a matrix that relates the nodal forces to the nodal responses. Okay. Okay. And the way it forms this relationship is through the physical and geometrical properties of the physical system. Okay. And so, it serves the exact same purpose of the spring constant in Hooke's law that we talked about earlier today, okay? Except now it's just in matrix form, right? And so, with the springs, it might look really trivial. And so it seems like we kind of went through this long kind of convoluted derivation only to arrive at, a matrix of Ks. But, the spring is kind of the simplest form. And so, starting next week, where we're going to talk about beams, you'll see that the beam, or not beams, a truss element or bar, okay? And so what you'll see for a bar is that even though a bar doesn't have, a spring constant for the bar, we can still form an element stiffness matrix, that's comprised of the, material properties and the geometric properties of the bar itself, okay? And so the concept of element stiffness is going to be, used throughout all of finite elements, okay? It's just the entries that go into the element stiffness matrix will change depending on, what the physical system is. All right. Any questions on this? Okay. And so that's the whole idea behind an element stiffness matrix, okay? Right. And so, kind of bringing this back to our finite element methodology, right? And so remember that when we produce a finite element mesh, right? And so when you ask ANSYS to produce a mesh for you, it produces a mesh with, hundreds, thousands, tens of thousands of elements, right? And so out of those many, and so what I'm saying, let me say this again. So each of those many elements in the finite element mesh is going to have its own element stiffness matrix. Okay. Right. And so 99.9% of the times, each of those elements are going to have a different element stiffness matrix, right? Or so the entries are going to be different because it depends on the geometry of the elements themselves. It depends on the material properties there. It depends on a lot of things. Okay. And so, we're starting out with a very simple system of a spring, which has just one spring constant. But in reality, the element stiffness matrix incorporates a lot of different factors. Okay. All right. And so that's element stiffness matrices. And now let's start talking about assembly. Okay. All right. And so building off this idea that each element has their own element stiffness matrix, in the end, we're going to have to combine these into one system. Okay. Because we have to basically solve, one system at the same time, right? And so when I talk about assembly, what I really mean is assembly of the element stiffness matrices from all the different elements of the system. Okay, and so this is assembly of multi-element systems. All right. And so let's go ahead and take our spring system and add one more spring here. And so now there's two of them, okay? And so I've drawn the dots here, which are going to be all the nodes. Okay, so that's node 1, node 2, and node 3, okay? And let's say that this spring right here, the first one, has a spring constant Ka, okay? Meanwhile, the second spring has a constant Kb, okay? And then at node 3 right here, let's say that we're applying a tensile force F, right? And so just like we did before, each of these nodes here are going to have a nodal displacement. Okay. And so it's going to be D1, D2, and D3, okay? And the goal for this is to solve what all those displacements are given the spring constants and the external force, okay? All right. And so the complicated thing with this setup here, compared to our last one is, obviously now we have 2 springs instead of 1, okay? But each of these springs will still have their own element stiffness matrix, right? And so for spring A, and so we'll call that element A, okay? And so the element stiffness system for this is going to be F1, F2 is equal to Ka minus Ka minus Ka, Ka times D1, D2, okay? And then for the second element here, right? The second element here, it acts on nodes 2 and 3, and so we have to change the numbering accordingly, okay? And so for node B, we're going to have F2, F3 is equal to spring constant for spring B is going to be KB. So we have KB minus KB minus KB, KB. Okay. Oh, sorry. And so this is going to be multiplied by K2 and K3. Okay. All right, and so we have 2 elements, and so we have 2 element stiffness matrices, okay, and 2 elemental systems. And so before we can actually solve this, we have to combine this together into one system. Okay. Okay. Because remember what I said about these systems, that they're all coupled, right? And so the solution at node 1 is going to depend on the solution at node 2, which is going to depend on the solution at node 3. Okay. And so in order to get a fair solution for this, we can't just solve for 3 first and then go to 2 and then go to 1. And so we have to solve everything at the same time. And so in order to do that, we have to have one giant system that encapsulates all these things. Okay. And since we have 3 unknowns here, that means we need to get a global system which is comprised of 3 different equations. Okay. But what we have instead of 3 equations for our 3 unknowns, what we have are these kind of 2 smaller dinky systems. Okay. And so the goal of assembly is to basically take all the little elemental systems and then assemble them into one big, what I call global system. Okay. Okay. Any questions on this so far? Okay. All right. And so in the end, we want a system that looks like this. We have F1, F2, F3. Okay. Then we have our, global stiffness matrix. Okay. Okay. And then we have D1, D2, and D3. Okay. And then just to make things a little bit easier, I'm going to label, you can think of D1, D2, and D3 as labeling the rows, okay? But I'm also going to label the columns as well. Okay. And so I'm going to label the columns D1, D2, and D3 as well. Okay. All right. And so the objective here is to, find out, what's going to be in this blank matrix here, okay? Because this blank matrix is known as the global stiffness matrix. Right. And so we need to find out what's in the global stiffness matrix, keeping in mind that we have all the individual element stiffness matrices. Okay. All right. And so the way this is going to work, and so the way that assembly works is that after we solve for all of the individual element stiffness matrices, we can then just simply insert them into their proper locations into the global system. Okay. And so it's literally just kind of fitting together pieces of a puzzle, right? And so the idea is just to find out which location are we going to insert these elemental systems in. Okay. All right. And so the way that you determine, what location that they go into, it all depends on which nodes that they act on. Okay. Okay. And so let's take element A as an example. Okay. And so element A, it's acting on the left side of the domain. Okay. And so this means that it's going to be acting on nodes 1 and 2. Okay. All right. And so since element A acts on nodes 1 and 2, let's go ahead and fill that in for all the locations in the global system that interact with nodes 1 and 2. Okay. And in particular, I'm going to use green for element 1 right here. Okay. Okay. And so if I draw this kind of dotted box around here, okay, and you kind of look at what rows and what columns this encapsulates, right? Right. You can see that this box right here covers all of the node 1s and node 2s, right? And so you can see it interacts with D1 and D2 on the rows, and it also interacts with D1 and D2 columns as well. Okay. And so that's how basically you determine where the element stiffness matrices go in. Okay. Is by looking at what nodes that they interact with. Okay. And then filling in that exact spot in the global system. And so that's going to be element A, okay? Right. And then next we have element B. And so element B, we can see from here, interacts with nodes 2 and 3, okay? And so that means that the location for element B is going to be everything that has to do with nodes 2 and 3, okay? And so if we look at our rows and columns, we can see that nodes 2 and 3 is going to be the lower right quadrant of this global system. Okay. Right. And so to determine these locations, remember, you just look at what nodes that they interact with and then just fill them in appropriately. Okay. All right. And so what I'm going to do next on the next page, just because I didn't have that much room here, is I'm actually going to fill in, the values for, element stiffness matrix A and element stiffness matrix B. Okay, because right now I've just kind of put placeholders for them, because I've just said that, you know, element A is going to go in this green region, and then element B is going to go in that blue region, but we haven't actually filled in the values for these just yet. Okay. So any questions on this so far? Okay. All right. So let's go ahead and fill those in. All right. So let me go ahead and draw the matrix here bigger, just so I have more room to write. All right, so let's start with element A, right? So we know element A is in the upper left coordinate quadrant because that's because it's interacting with nodes 1 and 2. Right? So we go ahead and draw in the dotted lines. Okay. This is all for element A. Okay. Now let's go ahead and fill in the values for element A. Okay. So we know element A has a stiffness or a spring constant of Ka, as we have Ka minus Ka and Ka, right? And then element B is going to be in the lower right quadrant, okay? All right, and so element B is going to be, you know, in this blue box here, right? And so for element B, you know, our spring constant for that one is going to be minus Kb minus Kb, Kb, okay? Right. And so if you notice here, you know, we have one overlap. And so we're overlapping here on the D2 spot, okay? And so when two element stiffness matrices overlap like this, you know, what you basically have to do is just simply add them together. Okay. Okay. And so in that 2 spot right there, we're going to have Ka plus Kb, okay, because that's just where they overlap. Okay. All right. And so those are those entries, okay? And so if you'll notice also that we have 2 entries here that are not claimed, right? And so the entry in the top right and the bottom left we don't have that crossing any element stiffness matrix, okay? And so what we put for those areas is that we just simply put a 0, okay? All right, any questions on this so far? Okay. All right, and so we're in good shape right now, because remember what we wanted was, you know, we started out with this 2-spring system, 2 springs and 3 nodes, and then what we wanted was just a single 3x3 linear system where we can solve for D1, D2, and D3 at the same time. Okay, and we got that, right? And so through you know, making the element stiffness matrices and slotting them into the right locations for the global matrix, right? We ended up with exactly what we wanted. And so we have 3 equations here. And so we have the F1 row, we have the F2 row, and the F3 row, right? And so each of these are the 3 equations, okay? And our 3 unknowns are D1, D2, and D3, right? And so, you know, the next logical step here is to take this system and solve it for D1, D2, and D3, okay? And so for matrix systems like these, you know, and this is a very modest case, and so we only have 3x3. But you know, in reality, you know, especially for the things ANSYS is solving, you know, this matrix right here would be something on the order of like, you know, maybe like 200,000 by 200,000, right? And so, you know, I know that you've all probably taken it in linear algebra class, and you know how to solve these by hand. You could probably do like an LU decomposition and maybe do pivoting and all that stuff. Okay. But for finite element problems like this, it's just not practical, because you're going to end up with, you know, even with simple hand calculations, you know, you'll probably have some homework problems where you have like a 20 by 20 system, right? And that's just not practical to solve by hand. Okay. And so the way that we typically solve these is we basically recognize that it's a matrix, okay? Okay, and so we have an F vector is equal to K matrix here multiplied by D vector, okay? Right. And so, what we can do to solve this is we could just multiply by the inverse of K. Okay. And so we're going to multiply both sides by K inverse, right? And so by on the left-hand side, we're going to have K inverse F. Okay. And on the right-hand side, we're going to have K inverse multiplied by K. Okay. This right here is going to cancel out and become the identity matrix, right? And so that's the definition of the inverse. And so if you multiply a matrix by its inverse, you get the identity matrix. Okay. And multiplied by D. Okay. And so in the end, what we get is K minus 1 times F vector is equal to D vector. Okay. Right, and the way that we compute this inverse is we usually just let the computer do it. And so for the homework problems I'm gonna give you for in this section, I'm just gonna tell you just solve this system using MATLAB. Okay. Right. And so I know that MATLAB is not a required course for this prerequisite for this course, but it's really simple. And so I know some people kind of get jittery when I mention MATLAB, but it's really simple, and the only purpose MATLAB is going to serve here is just to save you just a ton of work. Okay, and so basically all you're going to have to do is just input these matrices in MATLAB and then just run the inverse command, and that'll compute the inverse for you. Okay. All right. Any questions on this so far? Okay. All right, and so you would think that now that we have it in this form, we're good to go, right? And so all we have to do is form the global stiffness matrix, form the inverse, multiplied by the F's, and then that's it, right? Unfortunately, if you look a little more carefully at this matrix right here, okay, if you look a little bit more carefully at this matrix, you'll notice that it's a symmetric matrix. Right, and so if you kind of put a line down the main diagonal there, you'll notice that it's the same across both sides of the diagonal. Okay, and if you try to take an inverse of a symmetric matrix like this, you're going to have a bad time. Or in other words, even MATLAB is going to say that I can't do this because it's a symmetric matrix. Okay, and we have another issue, right? The other issue is that we have these random F's floating here. Okay, presumably we're supposed to put something in for these F's because they're going to be inputs for our problem, but we haven't done so yet, right? So right now they're just kind of arbitrary F's that are still just kind of floating around. Okay, and so we need to tackle both of these issues at the same time. And so we need to make our linear system actually invertible, right? And so we need to make sure it's we can actually apply an inverse. And then we also need to input values for our forcing vector on the left-hand side. Okay, and so the way that we're going to solve both of these issues at the same time is by applying boundary conditions to our simulation. Okay. All right, and so even though we're doing kind of these simplified 1D finite element problems, they still are finite element problems at the end of the day, right? And so just like in ANSYS, you can't run an ANSYS simulation without applying boundary conditions. And we're going to have to do the same here as well. Okay. All right, so let's talk boundary conditions. Okay. All right. And so I think, this part I think will be pretty cool and pretty interesting because, you'll actually get to see, what happens, when I apply a fixed constraint, what happens when I apply a pressure load or a force load, right? And so what is ANSYS actually doing with that information, right? And so this will kind of help shed some light on that, okay? All right, and so before we begin, so let's kind of remind ourselves what boundary conditions are. And so boundary conditions are simply all the external effects that are having, an influence on your structural physical response. Okay. Okay. And back when we first talked about boundary conditions, we classified them into two categories, right? And so we classified them into constraints, constraint type boundary conditions. Okay. And then we also classified them into load type boundary conditions. Okay. All right. And so do you all remember the kind of the alternate name I gave for these? And so the kind of the convoluted mathematical name. And so I'm going to put them again here because I'm going to refer to them as kind of their mathematical name, just because it's these are kind of the mathematical problems. Okay. And so for constraint type boundary conditions, I call these Dirichlet boundary conditions. Okay. And then load type boundary conditions, I call these Neumann boundary conditions. Okay. And so D and N boundary conditions, right? And so I'm still going to try to call them constraint and Neumann, or constraint and load type boundary conditions. I just kind of did it unconsciously. But if I use the terms Dirichlet or Neumann, then this is kind of what I'm referring to. Okay. And so it's a little bit hard for me because I've been trying to use these terms constraint and load type just because I know they're more physically intuitive. But just the way I was trained and kind of the way it was kind of drilled into me, when I learned this stuff was I learned Dirichlet and Neumann, and that's a little bit hard to kind of unlearn from that. And so if I slip up and say Dirichlet and Neumann, this is kind of what I mean from that. Okay. All right. And so I'm not going to go really into the definitions for these types of boundary conditions, just because we've kind of seen them before, and you kind of know what kinds of effects they have on the solution. Okay, and so I'm going to go ahead and jump right into how do we apply these in the mathematical sense. Okay. All right, and so let's go ahead and look back at our geometry and our situation for this two spring case. Right. And then let's characterize the effects at the two end nodes, and characterize them as in terms of what types of boundary conditions that they are. All right. And so here's our physical system again. And so we have 3 nodes and 2 springs. Okay. Again, this is spring A, this is spring B, okay? Right, and so our 2 boundary nodes here are going to be node 1, okay, and node 3, right? And so you can kind of see already from this image here that we have constraints and loads being applied on these nodes already, okay? But let's go ahead and go through each of these individually and characterize what kinds of boundary conditions that they are. All right, so let's start with node 1. And so node 1, you can see here, is attached to a wall. Okay. And so we can see from this image here that this is going to be a fixed support. Okay. Whereas on the right-hand side, we have a force that's being applied, right? And so we're pulling the springs over to the right. And so this here is going to be a force load. Okay. And so if we relate this back to our types of boundary conditions that we have, we can kind of clearly see that node 1 here is going to be under a constraint type boundary condition. Okay. Or Dirichlet type, okay? And then clearly on the right here, we have another boundary condition, and this one's going to be a load type boundary condition, okay? All right. And so the question now is, now that we've correctly identified, what types of boundary conditions that we have, how do we actually formulate this mathematically and incorporate that into our global system? Okay. Okay. And as we kind of do the mathematics behind these, you'll kind of see why I make this distinction between the constraints and the loads, right? Because if you're just using kind of ANSYS just by itself, the constraints and the loads, I think it's kind of nice trivia to know the difference between them. But besides that, you kind of know most of the time that it doesn't really matter all too much, right? The only thing that I've kind of taught you guys up to this point is that you need to have at least one constraint type, right? But besides that, there's not that much difference, at least in terms of how they're applied. Okay, but what you'll see is that mathematically there is a big difference in how they're applied, and which is why they have kind of two very distinct names. Okay. All right, but I think because we're just about out of time, I'll do a cliffhanger here. And I'll say that, we'll look at these mathematically on Thursday. Okay. All right. So any final questions before we wrap up for today? Okay. All right. And so that's all we got time for. And so I apologize again for kind of the last change to virtual. And, if you try to get into the computer lab and it wasn't open, I'm sorry for that. Right. And so I'll make sure to send another reminder to the department on Thursday to make sure that they open the computer lab for you guys, if in case you want to work on the project. Okay. And so usually I ask them to open up in the morning, and then it's open kind of throughout the day as usual. Okay. All right. So thank you guys for tuning in. Hope you guys enjoy the rest of your evening, and I will see you virtually on Thursday.
Thank you, Professor.
Yep. Mm-hmm.
Thank you, Professor.
Yep. Yes, actually, yes. Good question. So question from Isaac is that, do we assume that the entire bridge is made of steel? Yeah, and so I didn't have you change anything with the materials in this assignment just because there was a lot of other stuff going on. And so, yeah, you can just assume that the entire bridge is made of structural steel. Yeah, but in reality, you would definitely change the material to something more realistic, like asphalt or concrete for the road. Yeah, definitely. Hmm?
Thanks, Dr. Tran. You have a good one. We'll see you on Thursday.
Thanks, Stephen. Yep, see you Thursday.
Thank you, Dr. Tran. See you
Thanks,
on
Jasmine.
Thursday.
Yep, see you.
Bye.
I see you again.
Yep.
Enjoy your evening.
You too.
Hello?
Hi.
Oh yeah, I have another question.
Sure.
Activity number 4.
Sure.
And then